second lecture. This is the part on optimality conditions. Is the sound okay? Hello? Okay, better now? Yeah? Okay. So, this second part, we will do a proof of the KKT conditions. It's an algorithm proof. You can find it on the book of Bertsekas. And then I will focus on some other optimality conditions called sequential and some discussion about some algorithms. Okay, so we begin. We begin by defining the problem. We have here a general nonlinear programming problem. The difference now is that I have some general constraints here. So there are the same M equalities and P inequalities, and this additional constraint set that X must belong to this closed set omega bar. Okay. So I must mention that I decided to skip the end of the last part about interior point methods. So it was mainly some basic material about linear programming interior point methods. So you can read the slides or you can check other reference about this content. So I will focus here on the external penalty method. So let's recall we had a sequence of parameter rho k, penalty parameter, and for each k we can solve this subproblem. So now it's not an unconstrained subproblem, it's an easy constraint subproblem. So we selected those constraints in omega bar, and we will not penalize with respect to these constraints. So in external penalty methods, you can always do this. You can select some constraints that you think that they are easy to solve, and you penalize with respect to the difficult constraints. So if you have an algorithm that is able to minimize functions under this constraint omega bar, you can do this strategy. So you can think of this omega bar as linear constraints, for example. So we will use this idea to give a proof for the KKT condition. So we will choose this omega bar according to our needs. So in each iteration of the external penalty method, we want to obtain a global solution xk of this problem, if it exists. Maybe this set omega bar is unlimited, unbounded, so maybe there is no solution. But if it exists, you call it xk, and you generate an iterate for this method. It's interesting to note that you can assure existence of this global solution xk simply choosing this set omega bar as a non-empty compact set. So we previously assumed that it was closed. Now, if you want to guarantee existence at each solution, at each iterate, you can impose that it's a non-empty bounded set. And the penalty function, we will choose this one. Okay. So this is the two theorems that we will prove. So the first one is about the feasibility of the limit points. So if this sequence xk is well defined, so it may converge or it may not converge, but if it has some limit point, we will prove that every limit point of this sequence is a global solution to this problem, to minimize the penalization function p subject to this easy constraint omega bar. So we can't prove that these limit points are feasible for the problem. And this is because a feasible point may not exist. Okay, this penalization, these constraints may be such that P of x is never 0. If you remember, P of x is this function. In fact, we will not use this particular form of function P. We will simply need to know that P of x is non-negative and it is 0 if and only if you are at a feasible point. Okay, so we will prove this first one. And the second one is about optimality of feasible points. So if the sequence is well defined, and if in addition you have a feasible point for your problem, the feasible region is not empty, then you can prove that limit points of this sequence is in fact global solution to the original problem. Okay, so let's start with the first one. We are assuming that this sequence is well defined, and then we have to prove something about every limit point of this sequence. So we will take one limit point, let's call it x star. Okay, so maybe I should write it down. So we have here a limit point, so let x star be a limit point of this sequence. So this means that we can have a subsequence. So there exists some index of some subset of indexes. So there is some index K1. It's an infinite subset of natural numbers, such that if you write this sequence xk with indexes in this subset, K1, this is a convergent sequence. Okay? You have a convergent subsequence if you can choose some indexes of this sequence such that if you choose this particular indexes, you have a convergent sequence. So this can be easily done. I can assume that the whole sequence is converging to this point x star. In fact, we will simply write xk converges to x star. We simply rename the sequence. Note that in this algorithm, the iteration, the point xk plus 1 does not depend on the point xk. So in fact, for each k, you can simply find xk, and it does not depend on the previous ones. So this is done simply because in implementation, it is easier if you use xk as an initial approximation for the solution of the next problem. But theoretically, you can only solve each problem for each k. And so if you rename this sequence whole k, you can get a convergent sequence. Okay, so you have a sequence xk converges to x star. So xk is chosen as the solution of this problem. Okay, so we are assuming that this solution exists. So in particular, xk must belong to this set omega bar. Okay, so xk belongs to omega bar. And of course, this implies that x star is also in omega bar, because we are assuming that this is a closed set. And a closed set, by definition, it contains the limit of every sequence defined in the set. So x star must be in omega bar. Okay, that is some progress. And so x star is a feasible point for this problem that we are trying to prove that it's a global solution. So it's a good start. So let's prove that, in fact, x star is a minimizer for this function p of x over every point in omega bar. So we will assume that this is not the case. We will assume that there is some z feasible for this problem with such that the objective function is less in z than it is in x star. So assume there is this point. Then you can find this constant c. It's positive constant. So this is p of x star is strictly larger than p of z. So you can think that it is larger than something like this must hold. It's greater than p of z plus some positive constant c. So since p of xk, since xk is converging to x star, p of xk is converging to p of x star. Since this function, we assume that it is a continuous function. So we must have this inequality here, 3. P of xk should be greater than p of z plus c for some constant c, and if you choose k sufficiently large. So we have some algebraic manipulations here. We simply multiply this by whole k, and we add f of xk on both sides. Okay, we multiply this by whole k, we get whole kp of xk is greater than whole kp z plus whole kc. Now we add f of xk on both sides, and we add and subtract f of z here. Okay, so we have this inequality. So let's see that this must contradict the minimality of xk, the definition of xk. Remember that xk was defined such that this function is the least value it could assume. So we are proving that it is greater than this number. That is, this is the same function evaluated at z plus this term. So this term, this is converging to f of x star. So this is bounded by some constant, and this is unbounded. Whole k is going to infinity, and c is positive. So in particular, this term must be positive for sufficiently large k. So we have something like this, f of xk plus whole k, p of xk, this should be greater than f of z plus whole k, p of z, plus some positive terms. So in particular, it is greater than this number. So for sufficiently large k. So this is a contradiction, because z was assumed to belong to this set omega bar, and its function value is less than the value at the global minimum for the subproblem. Okay? Any doubts here? Are you following? Okay. So we established this result. let's look at the optimality of limit points. So if the problem admits a feasible point, you are going to limit points will be feasible, and now let's prove that they will be optimum to the problem, to the original problem. Okay, so the proof is easier. You have again xk. You can choose a subsequence such that it converts to x star, some limit point of the sequence, and it must belong to omega bar as before. And now if you do this calculation, you have that OK p of xk, this is always non-negative, OK is a positive number, and p is a non-negative function. I don't know if xk is feasible or not, so this may be positive. So in particular, we have this first inequality here. And by the definition of xk, this is the least value of this function f plus OK p. So if I take any other z feasible for the subproblem, we must have this inequality. Okay? So I shall look at what happens if I choose z, not only belonging to omega bar, feasible for the subproblem, but also feasible for the original problem. Okay, so let's only look at feasible points z for the original problem. For this point z, h of z is 0, and g of z is less than or equal to 0. So, and the function p is defined in such a way that p of z is 0 if z is feasible. So this term vanishes now. If I choose feasible z's, p of z is 0. So we have this inequality, f of xk is less than or equal to f of z for every feasible z's. Okay, so if I take a limit now in xk is converging to x star is feasible, I have already proved this, so we show that f of x star is less or equal to f of z for every feasible z, and x star is a feasible point. So x star is a global solution to the original problem. Okay? If you don't understand something, please let me know. All right, so these are two main theorems about the external penalty method. So it works, at least theoretically, it finds a solution of the problem. So we will use these theoretical properties to build a particular problem where we can control these sequences, and we will show that KKT conditions. So consider now the problem without this additional set omega bar. So I have the original nonlinear programming problem, and let's assume that x star is a local solution. Okay, so we want to prove KKT condition, that is a necessary condition for optimality. So I want to study, if I have a solution, x star, what happens with this solution? What can I say about it? So I assume I have initially a local solution. So let's build this artificial problem, and we will apply the external penalty method to this artificial problem, let's say regularized problem. So I built this problem in this way, such that x star will be the unique global minimizer of this problem. So we see that I've added here an additional constraint. This constraint simply says that I'm looking only at a neighborhood of x star. So this local solution, x star, when I add this constraint for sufficiently small delta, X star will be a global solution for this problem. Okay, for every feasible point now, the value of the objective function must be smaller in X star than in any other feasible point, because I'm constrained the problem to only see this neighborhood where X star was a local solution. Okay, so if I simply added this constraint, I would have X star is one global minimizer of this problem. But I wouldn't be able to show that it was a unique global minimizer. So if this problem could have more than one global minimizer, X star and some other value. But if you have two global minimizers, the objective function must be the same at these points. It's the lowest possible value that the function assumes for feasible points. So if you have two values that attain this minimal value, this must be the same value. So if I modify the objective function in this way, I can guarantee that X star is the unique global minimizer. Because if I had some other global minimizer, this objective function will be greater than it was in X star. So it's an artificial problem that depends on the local solution, but okay, I can apply theoretically the external penalty method to this problem, and I know it has a unique global minimizer. So this will be important. And I will choose as omega bar this set here. Okay, this additional set this additional constraint, I will consider it in omega bar, so that I will not penalize this constraint. So the subproblems for the external penalty method will be like this. This is my new objective function. I penalize it with the function p of x that looks at the equality constraints h and inequality constraints g, and it's constrained to the set omega bar. So let's prove that xk is well defined, and in fact it converges to X star. Okay, so well defined, we get well defined of this sequence because this constraint is it's a compact set. Okay, so it's non-empty compact set. X star belongs to this set, and it is compact. So you get well-definedness by Weierstrass theorem. In particular, the sequence xk that is well-defined, it always belongs to this set omega bar. It's defined as the solution for the parameter rho k. You get the solution rho k, that is the solution xk that is a feasible point for this problem. So in particular, we have boundedness of this sequence. All the sequence xk must belong to this ball around X star. So it's a bounded sequence. So you know that there is at least one limit point. So this is the Bolzano-Weierstrass theorem. Every bounded sequence has a convergent subsequence. So you know that there is at least one limit point. So, but what we know about this point X star, there is at least one limit point. Okay, so if there were some other limit points, so every other limit point of this sequence, it should be a global solution for this problem. Okay, we have proved that external penalty methods generate sequence whose limit points are global solutions when the feasible region is not empty. So every limit point is a global solution, but there is only one global solution. So it must have only one limit point. Okay? So in fact, this sequence xk is a convergent sequence, and it converges to the global solution to the problem. Okay, so this xk is convergent, and the limit must be the global solution that we know that existed. It was unique. It was x star. So we get this convergent sequence to the global solution. Okay, so now let's go back here. I have these are the sub-problems. So for each k, I solve this and I get xk. And this parameter delta was previously fixed. It's sufficiently small, but fixed. So since xk is converging to x star, this constraint will be inactive for k sufficiently large. Okay, so xk is getting closer and closer to x star as k goes to infinity. So this difference will be strictly less than any delta that I choose here. Okay, so in particular, this will hold. Xk minus x star is strictly less than delta. So xk will be a local solution to this unconstrained problem. Okay, so if I have xk, a solution of this problem, it has only one inequality constraint. And I know that at the solution, this constraint is inactive. I can simply get rid of this constraint. As we have done before, we can do this here again. Xk, if I look locally around xk, this will be a local solution of this unconstrained problem. Okay? So I will use what I know about solutions of unconstrained problem. So if I have this, I want to minimize this function. I know that xk is a local solution. So I know in particular that the gradient of this function is 0 if I look at xk. So let's call this function phi k of x. So at xk, this gradient of phi should be 0 when k is large enough. So now we will look at this particular formula for p. This is the first time that we need to look at this formula. Everything we've done before holds for any other function p. So if you have this function, we can compute its derivatives. So let's compute the derivatives of phi k. So derivative of f is the gradient of f at xk. The derivative of this thing here is simply the sum of the squares of the difference xi minus x star. So when I compute derivatives, I have this vector here. And now it's whole k times the derivative of p. So the derivative of p is simply the sum of the squares of hi. So you will have something like this. 2 times hi at x times the derivative of hi. Okay, this is the chain rule for the derivative of hi of x squared. 2 times hi of x times the derivative of h. So if you add everybody here, you get this. And you have to compute the derivative of this part here. So it's similar. You have 2 times, it's the sum of this maximum squared. So you have 2 times this maximum times the derivative of g. Okay, these squares are there so that this part of the function is differentiable. So you can compute its derivative in this way. Okay, so we are almost there. Okay. So look here that xk is converging to x star. So this is going to the gradient of the function at x star. this is going to 0. This, I don't know what happens here, because whole k is going to infinity, and hi of xk is going to 0. Xk is going to x star, and x star is feasible. So I don't know what happens here. But this is going to the gradient of hi in x star, and this also is going to the gradient of this constraint. Okay, so what we do, we call this an approximation to the Lagrange multipliers at the solution. And this is an approximation for the Lagrange multipliers of the inequality constraints. So let's define these approximations, lambda I and mu j. And we note that this approximation mu k is always non-negative. Okay, it's defined by this formula, whole k is positive, and this maximum of 0 and something, it's non-negative. So it's a good thing that the approximation for the Lagrange multipliers associated to the inequality constraints is a non-negative number. And we note some other thing. If I have an inactive constraint, if at the solution gj of x star is strictly smaller than 0, this formula will result in 0. Okay, if I have k large enough. Okay, so at the limit you have a convergence sequence, xk converges to x star, and at the limit it has a non-negative value. So if k is large enough, gj of xk must also be a negative number. So when I take this maximum of 0 and a negative number, I will have 0. So the multiplier associated to this constraint gj will be 0. So this is an important property to get KKT conditions. If I have an inactive constraint at the solution, the multiplier must be 0. You shouldn't consider constraints that are not active at the solution. So what we proved is this following theorem called the approximate KKT theorem. If x star is a local solution, it's a local minimizer of the original problem, we were able to find sequences xk, lambda k, and mu k, such that xk converges to x star, mu k is non-negative. I don't know if they converge, lambda k or mu k, I don't know. But I know that if I plug it here, this sequence on the gradients of the Lagrangian function, so remember the Lagrangian function was f of x plus the combination of the constraints and of equality and inequality constraints. So if I plug it here, I will have complementarity will hold. These multipliers will be 0 if I'm looking at an inactive constraint. So I can compute this sum only on the active index of constraint, inequality constraints, in the limit point x star, and this will go to 0. Okay, because of this formula here. This is our lambda k, this is our mu k, and this term here is going to 0. So everything else must go to 0 also, because this is equal to 0. So this is almost the KKT condition. It is not quite what I defined in the previous lecture, but it's quite similar. Okay, so in order to get a KKT condition, in fact, we must be able to prove that these sequences of lambda k and mu k, they are convergent, so that we can take limits here, and this will be a you will find the Lagrange multipliers lambda and mu associated to the limit point x star. So, but maybe this does not hold. So it's interesting that we are able to prove approximate KKT conditions even without any condition on the problem. Okay, so you can in fact use this condition as a necessary condition for optimality. Okay, you don't have to study the condition on the limit point. If you are able to find such sequences, then this is a good this indicates that your limit point it's a good candidate for a solution, because every solution x star must be such that there exists such conditions. So it is an optimality condition. Okay, even if I can't take the limit here and I don't get a KKT point in the limit, but the existence of these sequences is a necessary optimality condition. So I studied these conditions during my PhD, and we were able to prove that these are in fact good optimality conditions, because it's easy to define any optimality condition. So if x star is a solution, what can I say about it? I can say that it is a feasible point, for example. Okay, this is an optimality condition, a necessary optimality condition. Every solution must fulfill this condition. But is it good? Can I find solutions looking at these conditions? Well, in this case, no. But this kind of approximate KKT condition, they are good necessary optimality condition. You can, in fact, solve problems and get good candidates for solutions analyzing these conditions. So I will get in more details about this in a minute. So, but let's prove the classical KKT theorem. And this is what it says. If I have a local minimizer, and at this point I can compute all the gradients of the equality constraints and all the gradients of active inequality constraints, and the classical hypothesis that we made to prove KKT condition is assume linear independence of this set. Okay, so if this set is linearly independent, so we are able to prove that x star is a KKT point. That is, I can find Lagrange multipliers lambda and mu. Mu is non-negative, such that this linear combination is 0. The gradient of the Lagrangian function, if I evaluate at x star, lambda and mu, I will have 0. Okay? So we will prove this by... Wait. Okay.
Sorry, I have a question. What about the case where chi x star is not 0?
Where? Here? At this condition?
Yes, you are not taking them into account.
Yes, we don't have to make it into account. In fact, as we saw in the previous lecture, the KKT conditions only take into account the gradients of the constraints that are active at the solution. If you have inactive gradients, you can simply get rid of it. It does not. You can eliminate it from the problem, and you will still have a local solution for your problem. So the inactive constraint should not be taken into account in any case. Okay?
Okay, thank you.
So my question is, my question is about the assumption in this theorem. It is not enough to have linear independence separately of grading of hi and grading of gij, or it is absolutely necessary to have this?
Yes, it's not enough to have separate linearly independent sets. You must have must take into account every constraint and treat them as equally, and this whole set must be linearly independent.
Okay, thank you.
In the next lecture, I will talk about how to prove this same theorem with weaker conditions. In fact, you don't need linear independence to prove this. And in our proof, we will in fact see that we don't need linear independence. We can assume something weaker. So we will prove this by using the approximate KKT theorem. So the assumption is that X star is a local minimizer with some additional thing. So I can use this approximate KKT theorem. I know that this sequence must exist. So I will work with this limit here. Okay, so there are these sequences, lambda k and mu k, and I want to take limits on this sequence. So if this sequence of norms is bounded, so we may choose a convergent subsequence, lambda k converges to some lambda, and mu k converges to some mu. So since this sequence is non-negative, the limit must also be non-negative, so this multiplier has the correct sign. And the result follows if I simply take limits on the previous condition here. Everything is convergent. So this converges to this. Okay, so this must be 0. So what we have to, we should use this linear independence condition to rule out the other possibility. So if mk is unbounded, so you have a sequence of Lagrange multipliers that is divergent, so we can choose a subsequence such that it in fact diverges. So it's not bounded, so we can find a sequence, a subsequence, a divergent subsequence, okay? So mk is divergent. So you can simply divide this previous inequality that we had. So here I'm not looking at the limit. So I call this thing epsilon k, okay? And this is going to 0. So I have this epsilon k, and I divide everything by mk, this divergent sequence. This is going to 0. So in particular, the right-hand side still goes to 0. Here, this is going to 0. Gradient of f of xk is a convergent vector. It's convergent to the gradient of f of x star. And if I divide it to a divergent sequence, this goes to 0. So the part that remains is this one. This combination is going to 0. But let's look at what happens here. So these sequences, these are bounded. This is a bounded sequence because I had this initial sequence lambda k mu k, and I divided it by its norm. So in particular, this sequence has norm 1 for every k. So it's a bounded sequence, unit length bounded sequence. So we may choose a convergent subsequence. So lambda k over mk converges to some alpha, and mu k over mk converges to some beta. So note here that since the norm is a continuous function, this vector alpha beta should have norm 1 also. Okay, because these vectors all have norm 1. They are convergent to some vector alpha beta, so the limit must also have norm 1, and in particular, it is non-zero. So this is a contradiction with the linear independence of all the vectors. So if I take limits now, this is going to alpha I, this is going to beta I, and this is going to 0. So note here that the sum is also always taken on the feasible, on the active set of the constraint. So I don't have to worry about complementarity. It is always fulfilled. And so that's why it appears the linear combination of every gradient of constraints. So this is a contradiction. Okay, so we prove the KKT conditions. So we note here that this beta here, since mu k was non-negative and mk was non-negative also, so this beta is non-negative. Okay, so in fact we don't need linear independence. If we assume that linear independence says that no matter which alpha I take here and which beta j I put here, I can only get the zero vector if I take all of them equal to 0. Okay, this is linear independence. But I can prove a stronger result. If I put any alpha here, positive or negative, or any beta here, positive, I must have 0 here. Okay, so this is what we call a positive linear independence. So this vector are positive linear independent, then we can prove the KKT condition also. So I could have linear dependent vector, so this alpha and these betas could be non-zero as long as some beta j is negative. Okay, if I had a situation in this case such that every non-trivial combination that results the zero vector is such that some beta j is negative, then I can also prove the KKT condition. This is what we call the Mangasarian-Fromovitz constraint qualification. So you replace linear independence by positive linear independence. We will get in this detail in the next lecture, but maybe I should write it down here. So it's the positive. So we say that a set of vectors is positive linearly independent if I have lambda I. Okay, let's use this notation. So this j must add here. So if this is 0 with lambda I any real value and mu j non-negative, then the only solution is the trivial one. So this is positive linearly independence. The linear independence doesn't have this condition here on the sign of mu j. So this gives a stronger condition. You must have 0 if you have these additional combinations where the sign is possibly non-zero and non-negative. So we can prove this condition under this weaker assumption, and this is what is called the Mangasarian-Fromovitz constraint qualification. Okay, so we will get to this a little bit later. I think it's a good time to make a break.
We make a short as the other day.